Good evening, ma'am.
Good evening.
What would be today?
Right. So we have started week 6, that is root locus based topics. Am I audible enough?
Yes, ma'am.
Yeah. So we have started solving problems on root locus based topics. So this Friday session today is going to be on the problem solving session, same topic, root locus only. So we can discuss few problems. We can start solving few problems. And if you have any doubts, you can ask me on the. And we can also have a discussion at the end of this session. I hope everybody would have been familiar with this. So let me just recall this topic once again, all the properties, then we'll move towards problem solving session. The root locus is a graphical method that helps to analyze and design the closed loop pole location as the gain varies from zero to infinity. Why do we need to do this is to see how the poles of a system move from one place to another in a complex plane when you change the gain k. So if you have a system like this, k into some zero you have, some poles I have, just by changing this gain value k, I want to see how the poles of the system moves in a complex plane. So why we are interested in this is if this is my plane, normally for let's take k equal to 1, my poles are here. And if I change this to 5, where will the new poles will be? Somewhere I'm taking here some. So if I increase this to infinity, how will my system look like? Like where the poles of the system looks like. Why this is important? Because the location of the poles determine the stability of the system. This is the important aspect. First important aspect. The second thing is it determines the transient response of the system. So based on the location of poles, it determines the stability and the transient response of the system. So we are interested in seeing how the changing the gain affects the location of the poles and thereby indirectly affects the transient response and the stability of the systems. Right. And if you have, if I take an example, for example, if P of S, I'm taking K into G of S, divided by 1 plus K into G of S into H of S. This is some common transfer function representation I'm taking. Here, first thing I want to do is using root locus. First, I want to do is stability analysis. If I want to do stability analysis using Wilcoxes, I will check if poles ever enter into the right half of the S-plane because stability, whenever the poles lies on the left half of the S-plane, the system would be stable. We have seen this before. And if it enters into the right half of the S-plane, it would be unstable. When it lies on the origin, we call it as marginally stable because this exhibits an oscillatory behavior that might change to either stable or unstable behavior based on the next gain change or any perturbation we are giving to that system. So this is equally dangerous as unstable. Unless we maintain that gain or all the parameters constantly, this will exhibit an oscillatory behavior or either fall into stable or unstable region so easily. So for our interest, the system should be always be stable. So that's our primary interest. The second thing I want to know is this design. First is stability, second is design criteria. So how well I want my system to behave. For example, if my system is exhibiting this overshoot, this kind of overshoot and oscillatory behavior and takes forever to settle. It takes for around 8 seconds to settle. If I want my system to give me a little less settling time, for example, I want it to settle by at least 5 seconds. So I can tune the system based on that by just changing the gain k value. That's the primary motive of this root locus technique without taking much effort to do that. So the first point I am interested in stability analysis, then the design criteria, right? Okay.
Yes, ma'am.
Okay. Then the additional thing we can study from this root locus is this. It shows the trade-off between speed and damping. So sometimes I I might push the system to be more stable, but I might exhibit a very fast or slower responses. So there will always be a trade-off between this pole location to ensure the stability and getting out the desired specifications, right? So using the root locus, we will find this trade-off very easily. In order to find every time, if you want to find the stability by taking a Routh-Horvitz or any other method, and instead of doing all those things, we can straight away use this method to check the trade-off between which will be the optimal position, so that my system would be stable and also will give a desired output specifications or a desired transient responses. So I would get to choose based on this root locus analysis. This is one of the time response or a time domain based analysis. Later, we will see more like frequency domain analysis, like Bode plots and Nyquist plots, and all. That will be in the upcoming week. So, this week we will be covering one of the techniques that comes under the time domain analysis. Okay. So far, we know why we are doing and what we are doing. Now we are going to see how we are going to do this method. There are some conditions for designing root locus based thing. Okay. First thing is magnitude conditions. Okay. Considering this representation of transfer function, this is k g of s by 1 plus k into g of s h of s. If so, the magnitude condition will look something like this. K into g of s should satisfy the magnitude of or absolute values of k into g of s into h of s should be equal to 1. This should always satisfy. This is the first condition, magnitude condition. The second condition is this angle criteria or angle condition we call. That tells angle of g of s into h of s will be 2k plus 1 into 180 degree, where k can vary from 1 to 0, 1 to etc. So, whatever design we do, it should always satisfy this two condition. This is an important rule in the root locus techniques. So, if I design a root locus, for example, if this is my root locus, something like this, arbitrarily I'm drawing. So, this root locus, all the points in this root locus will satisfy these two conditions. That's how this is being framed. So, if so, then the root locus is a valid root locus. So, you might be in asked like, if I give some diagrams, 2 or 3 root locus diagram, and if I ask whether this is a valid root locus, one of the first thing you have to check is whether it satisfies the angle of magnitude condition, angle and magnitude conditions. Right. Now we'll discuss few of the key properties of root locus. I'm just warming up on this. I hope this you've been familiar with this. You can just um, like tell along with me. The first thing is root locus always starts from open loop poles and ends in open loop zeros. If my g of s, h of s, if I give s minus s plus 4, and this will be s plus 2 and s plus 1. Let's take, okay? Now I've plotted two different root locus, -1, -2. Which one do you think would be the valid root locus here? A or B? I don't know how this happened. Something I changed or something. Okay, right. Hmm. Someone messaged, right? B. B. Gayatri is telling B. Someone, anybody has any other options? And Gayatri, why do you think the B will be the correct? Are you typing? Starts from poles and ends in zeros. Right. Let's go. So root locus should always start from open loop poles, and ends at open loop zero. The direction should be from poles to zero, and it will be never from a zero to pole. Okay, this is the first property, the root locus poles. Second one, inside this property, we should know that if the poles are less than zeros, some branches will go to infinity, right? Because if I have two poles and two zeros, any of this one pole will go to 1 0. The second pole, the second root locus will go from another pole to the second zero, right? If I have only one pole but I have two zeros, how can I manage this from this pole? One root locus will go to zero, any of the zero. It is based on the system's properties and the gain you are changing. Let's take this root locus is going to the zero. So from where this root locus will go? So this will, for this zero, the root locus will come from infinity. Similarly, I have 1 0, but I have two poles. I have only 1 0, but I have two poles. Then one of this pole will go to this zero. Any of this pole, either of this pole will go to zero. This will go to infinity. Is there any doubt on this?
So here you have written poles less than zero. That means number of poles should be less than zero. Then it will go to infinity.
Yeah, not value. It's number of poles less than number
Number
of
of
zeros.
okay. So then what's the above one where you have written two poles and two zeros when both are equal?
If I have equal poles and equal number of zeros. For example, I have two poles, two zeros.
Hmm.
Anyone can
Yeah.
go to anything. This can also be like this also. We don't know which one is going to which, but at least it will reach to a zero, that I know.
Okay.
But
But
here
if
only,
poles are less than zero, then it will tends to infinity.
yeah, if poles are less than zero, for that zeros, the how many number of poles are missing, that many number of root locus will come from infinity.
Okay.
For example, if I have two poles but I have only 1 0. For example, my 0 is here. It will occur in conjunct. My 0 is here, let's take. Okay, so a root locus can come from here to here. It always goes from poles to 0. So in this direction,
Okay, yes.
and there are another properties like your number of root locus should be equal to your number of poles. And root locus always starts from poles to 0. So I have 2 poles, but I have only written only one root locus now. So there should be another root locus, right? There is another property called about the real axis, root locus are always symmetry. That's what I'm going to tell to the as the next property. So if I dissect the S plane into two half about the real axis, for example, this is half 1 and this is half 2, my root locus will always be symmetry. If there is a one curve like here, there will be equal and symmetric curve here also. So about your real axis in the S plane, your root locus will be symmetric. So if I draw one root locus like this, there should be another root locus like this, right? If this property is true.
If it's symmetry
Yeah,
about
no, it's
real
always
axis.
symmetry.
Okay.
That's
Oh,
the
it's always
property.
symmetry. It's a property.
Yeah,
Okay.
it should satisfy. But there is only 1 0. There is no space for this to go. So what it will do is it will just go to the infinity,
Okay.
somewhere to the infinity. Arbitrarily, I'm drawing. You will get to know when we solve the real problems.
Okay.
Okay, correct. Just remember this property. We will verify whether it is working or not while solving the problems. Okay, right. So far, we know open loop. It starts root locus starts from open loop poles and ends at open loop zeros. And if some poles are lesser or some poles are more, then the rest of the things will come from or go to infinity. And next property is that your root locus, number of root locus branches will be always equal to the number of your poles, open loop poles. And the third property is that so far we have seen one property here, right? And this is the second one. And the third property is about real axis, root locus is always symmetric. Root locus is always symmetric about real axis. Okay, like this. So this is your imaginary axis, this is your cerebral. So about this, root locus will always be symmetric. Right. Fourth property tells a portion of real axis belongs to RL if the total number of real poles and zeros to the right of the root locus is odd. For example, if I have a pole here, I'm going to take a test point. So I will take a test point here. For example, T1. Anywhere you can take here, here. I will add 2, 3 test points. Okay. T4, T5. Okay. Let me start with T1. So if I look for a test point in the real axis and I'm seeing right side to that test point, and if I can find any poles and zeros, not poles or zeros, poles, summation of poles and zeros will be equal to R, then I will include this test point in my root locus trajectory, right? Otherwise, no. So if I look from T1, are there any poles or zeros to the right of this test point, right side of this test point? Are there any root poles or zeros? Someone answer, no?
So no, means these test points are zeros.
No, any poles or zeros lying to the right of this test point. For now, I'm taking T1. Are there any poles or zeros right to this
No,
test point in the real
no.
axis? No, right?
No.
Here also, in the entire axis I'm asking. Okay, there is no. So I won't
No.
include this T1 in my root locus. T1 won't be there in my root locus. Right. Then take
Okay.
T2. Now take T2 and check whether there are any poles are zero.
No. No.
No.
Neither for T2, not for T3 also.
T3 also. Right. No
Yeah.
root locus. Come to
Yeah.
the T4. Now see the T4. Are there any
Yes,
poles
there
and
is.
zeros? There is. How many poles and how many zeros are there?
So one pole is there.
One pole is there. Is it odd or even number?
But it's in real axis. So
That's fine. That's fine. Anywhere here would be applicable.
okay.
The number of poles lying in the right of the test point, is it odd or even?
Okay, so the number is odd. I mean, the number
Odd.
of poles is only one, so therefore odd.
So if it is odd, then I will take this test point T4 in my root locus. Check
Okay,
with T5,
so that's also for one.
one odd. So it will
Yeah,
come in
one
the
odd.
root locus. Now, so I have tested all my test points. So I'm saying this is my root locus.
Okay.
Agree? Because
Yeah,
other
agree.
than this, no other test points are there. Okay, let me give two more examples.
Wait. Okay. Yeah.
Now we'll say T1, T3, T2, T0. Now start with T0. T0 would come?
T0. No, there is
No.
nothing. Zero.
T1,
T1. No. Cross.
T2
One.
will come?
Odd.
Odd
Yeah.
number. T3,
Yes. Two poles are there, so it's even.
oh, so it won't come in the
So,
root locus.
so only for odd,
So
and it should be
only
right
this
side.
is in my root locus vicinity. Only here only my root locus can come. Any test points other than here will take two poles or even poles in the right of the S-plane root. Sorry, right side of the test point. So root locus won't come there. Oh,
And
if I
this fourth property is not about zeros, no. Only about this pole should we have to check.
no, this is a separate property we are seeing right now. We will do when we are solving problem, we will combine everything. I'm
Okay.
just asking question on this property right now.
Okay.
We many people will have doubts in this. That's why. So I'm taking this now. We'll check T1, T2, T3, T4. Right. Now, can you answer? T1 will come in the root locus.
Yeah, no.
T2,
No.
yes, because you have to see both zeros and poles
Yeah. Okay, sorry. Zeros
combining.
and poles.
So it will
Ah,
come, right? So this is a catch. If I take T3,
so then T3 will not come, but
will
T4
not
will
come
come.
because this is one pole, one
Even
zero
number.
added together, it will be two even numbers, so it won't come.
Yes.
T4,
It will come.
it will come, right? Good. So your root locus will look something like this. T2 will come and T4 will come, right? So your root locus will be this and this entire thing up to minus infinity.
Okay.
I hope this is clear. We'll do one more exercise. So now say which part will come from, okay, D1, D2, D3, D4. Right. Now say from
So
T1
T2 will
T1
come.
obviously won't come.
T2 will come,
T2 will come,
and
right?
yeah, and T3 will also come. So this I
Yes.
will take
Yeah.
this
Consider
along
this
the
as one
imaginary
pole.
axis.
Yeah.
2 poles.
1,
Yeah.
2, and 3. So it will also come. T3 will also come.
Then
But
T4 will not
T4
come.
will not
Will
come.
not
Right.
come.
Your root locus will look something like this. Okay.
Okay.
Now it's clear, right? This fourth property.
Yes. 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 Yes.
So whenever you take a test point on a real axis, if you see your right side, if you find odd number of poles and zeros combined, then that test point will come in the root locus, otherwise not. Okay.
Okay.
Fifth property is that a portion of a real axis belongs to RL if the total number of, okay, that's what we saw right now. Then we go for asymptotes. So from here, I will explain with the example because this is not a common thing. It's just a formula that we will solve using the problems. Okay, we'll go to problems. I'm taking an example. G of s, h of s is equal to k by s into s plus 2 into s plus 4. Right. The first step of finding a root locus is that find the location of zeros and poles and plot. Okay. So your zero location is no zeros. Poles lie at -2, 0, 4. Sorry, -4. So my plot will look like this: -2, 0, -4. Okay. Now we found the first step. First part is over. The second part is draw the or determine the real axis segment. Determine which part of it comes inside the segment. Whatever we did as a last property. So now I'm drawing over the same diagram. The second step it also. So I'm taking a test point here. I'm taking a test point here, here, and check. Okay, this test point would come. Will this come? T1 won't come because there is no other zeros or poles lies in the left of, right of that. T2, T3. So T2 will come because there is a one odd zero here. T2 will come. T3 won't come because there are one pole and another one pole is lying in, two poles are there right to the T3, and T4 will come because three poles are there right to the T4. So my root locus will be, this will come in my root locus vicinity, then this will come until it goes to -infinity. So this is my real axis segment of the root locus. Now I am going to find where this root locus will propagate when I change my gain k from 0 to infinity. This is my another next steps, right? Okay. So this green line is the part of root locus that belongs to the system.
Okay.
Okay. Next step is that identifying asymptotes. Why do we need asymptotes? Asymptotes show the direction. This shows the direction in which branches go to infinity. Particularly, why you're calculating asymptote in this question? Can you relate out of the properties we learned?
Mm, no idea till now.
How many number of zeros here?
0,
How many number of poles here?
3,
3 poles. So are there any zeros to for the root locus to go from open
Okay,
loop
no, no,
0
no,
to poles?
no.
No. So all the 3
So
will
poles are
go to infinity.
infinite because the number of poles is greater than number of zeros.
Number of zeros. So all the
Yeah.
poles originating, all the root locus originating from each pole will go to infinity. So that's why we are calculating this asymptotes. This asymptotes will
Okay.
tell in which direction this root locus will go to infinity. For example,
Okay.
it can go here, here, here. How there are infinite many ways to go, right? So this asymptotes will tell us particularly in which direction, but with the degrees, this pole will tend to go to infinity from the real axis. So to calculate that, the formula is that theta equal to 2k plus 1 into 180 degree divided by n minus n, where n is the number of poles and m is the number of zeros. Okay. So we have number of poles, we have that is n equal to 3, number of zeros we have that is n equal to 0. So n minus m will give only 3. 3 minus 0 equal to 3. Right. Now if I calculate theta, the k can vary from 0, comma 1, comma 2 kind of. So how many poles you have, that many k's you have to calculate. For example, I'm just rewriting this formula here. N minus m 180. I will just substitute whatever values I know divided by 3 into 180. So this will give me 2k plus 1 into 3 180 60, right? Sorry. 60, correct. So I have 3 poles, right? So I am going to, if there are 3 poles, the k will start from 0, 1 and 2. So this many k's I have to calculate. For first pole, 2 into 0 plus 1 into 60 degree. This will give me 2 into 60, 120 degree. Second is 2 into 1 plus 1 into 60 degree. This will give me 4 into 60, 240. The next thing is 2 into 2 plus 1 into 60. So it will give me 3 into 2, 6 into 6, 360. Right? So these are all the 3 angles my um, root locus is going to go from my real axis to infinity. Okay.
Yes, ma'am.
Okay, right.
So we will substitute k value as 0, 1, and 2.
Yeah. I think I made some mistake here. Let me check quickly. Correct. N equal to 3, 180, 60, 0. Okay. Sorry. This is a blunder. This is not 2 into k plus 1. This is 2k plus 1.
Okay, it's 2k plus 1. Hmm.
Okay, just rewrite this. Sorry for this. This is 2k plus 1. I have written it correctly here. Theta equal to 2k plus 1 by n minus m into 180. So this will give me 2k plus 1 into 180 divided by 3. So 2k plus 1 into 180, 60. When k equal to 0, 1, 2, because I have 3 poles. When k equal to 0, this will be 60 degree. When k equal to 1, 2 plus 1, 3,
180 degree.
180, 180 degree this will be. And this will
And
give me
300.
300 when k equal to 2. So these are all the 3 degrees. My root locus is going to go to infinity for my real parts of the system, real pole of the system. Good. That's correct. Now we know what this direction is going to go. I'm just going to copy this and put it there so that we can use it later. Paste. Okay. Now, from this poles, and we don't know from which pole it is going to go from 60, it's going to go from 180 and 300, right? Root locus can go like this, or like this. We don't know from which poles or from which direction. Like direction or degrees we found, and from which pole this degree is going to go, we are going to calculate in the next step. That's what the next step is. The next step is to calculate the centroid. How exactly it is going to split up your root locus, how exactly it is going to split up in the real axis, that will be given by this formula centroid. Zeta equal to summation of poles minus summation of zeros by n minus m. So your summation of poles is the summation of poles is speaking about the pole location. So you have poles at 0, minus 2, minus 4, right? So this is the summation of poles. Minus, I don't have any 0, it's simply 0 divided by number of poles minus number of zeros. So it will be 3 minus 0. So totally it will be minus 6 divided by 3 equal to minus 2. So your root locus is going to take a split at minus 2, exactly at this point. Okay, so this we found. The next we have to found is the now, as I said before, this we have poles in these locations, right? So we know since there are no zeros, it is going to approach infinity, and we found the degrees at which it is going to reach the infinity. So 180 degrees, something like this, 60 degrees will be like this, and 300 must be something here around 360 degree it will be. So these are the three direction it is going to go. But whether we know whether it will go from real axis to complex plane, or will it leave only here, or will it leave only to or will it cross the complex plane and go to imaginary axis, or it will go like this there. We don't know any of this thing, no. To know this exactly, we are going to find the breakaway and break-in points or break-in points. So far we have found third as asymptote, right? Fourth is centroid. Fifth will be breakaway or break-in points. So this breakaway or break-in will tell you where your root locus will leave the real axis and move into the complex plane. So your breakaway, calculating this breakaway or break-in point will tell you where this root locus is going to leave from real axis to your complex plane. That point it will tell you. The formula to find this is dk by ds equal to 0. So you have a k value or a gain value here, right? Where is our system? Here. So I'm going to differentiate this k with respect to s, differentiate your gain with respect to s, and equate it to 0. So this will tell me where exactly this root locus is going to leave from real axis to imaginary axis. Now we are going to calculate this step. how to do this? I have to first equate my this is like this. G of s h of s is equal to my um, some things that I have, right? G of s. Wait. G of s, h of s, I have given. This is my system. This is my system. Now I'm going to find this with and differentiate it with respect to this. So from this, I can rewrite as k equal to minus 1 by g of s into h of s will be equal to, if I keep j here and bring this here, my k would be equal to minus, this will come here and this will go here into h of s. This will be equal to minus s into s plus 2 into s plus 4. So you have this. If I calculate this, this will give me s into s square plus 6s plus 8. So minus s cube plus 6s square plus 8s. So this is k, right? So differentiating k with respect to s will give me minus of 3s square plus 12s plus 8. Now I'm going to equate this to 0. So minus 3s square plus 12s plus 8 equal to 0. I'll just keep this as positive. So I'll keep everything as negative and differentiating everything by 3s square minus 4s minus 8 by 3 equal to 0. So what root I will get? Minus 8 by 3
Ma'am,
should get,
everything is positive. That minus,
no.
you know.
So 1 minus is here, no? I'm multiplying it with minus, so this will also be minus, no? This will be
How much?
positive.
No, the step above that one bracket you missed.
Oh, okay, okay, okay. Wait, every time I'm doing this mistake. Right, right. Yeah, you're right. Then everything is positive means equating it will give you 0 only. So this will be, let's see, 3s square plus 12s plus 8 equal to 0. So a square plus 12 plus sorry 4s plus 8 by 3 equal to 0. So if I split this 8 by 3 into 4, I have to, how can I get 4 out of this? Uh, I should get positive, right? So this will give me, if I have to give 4, 12, 2 to 8 will come. Okay, let me just check with online. If you have calculator, you can calculate. Roots of a square plus 4s plus 8 by 3 equal to 0. Are you also getting something like this? This is equal to minus 0.7 minus 3.4.
Yes, ma'am.
Anybody getting this? Similar to this, right?
Yeah,
Some
minus
points
0.8, 0.85,
0.85 you're getting. This is 3.4 only.
3.15.
Okay, I'm just putting 3.2.
Okay, ma'am.
Okay. So your minus 0.8 minus, wait, is this equal to minus 0.8 minus 3.2 you have, right? So this is my breakaway or break-in point. So when do we call it as breakaway or break-in? Any idea? When do we call it as this point as breakaway, or when should I call it as break-in, or both are same?
When it goes to infinity, it's breakaway.
Okay, you can tell, but
I don't know, just guessing.
okay.
Breaking is when it comes to 0.
Okay. So breakaway, according to your guess, it is correct. It leaves real axis and goes to complex plane. For example, from this position, it is going somewhere in the complex plane. Then it is breakaway. Similarly, break in, it comes from complex plane and ends in the real axis. But importantly, when this will happen is breakaway will happen between two real poles. Break in, or this is come say breakaway will happen between two real poles. Breaking will happen between two real zeros. For example, if I found my breakaway point here, if I found a point, this S is equal to, for example, it is through minus 2, minus 3, this is 2.5. If I found my S is equal to minus 2.5, this is between two real poles, right? So I will call this as a breakaway point. 1 minute. I wanted to inform him something. Okay. Maybe I'll be here till 3:30. Okay. He will come with me. Then can you please inform him something? I'll just keep it here. Okay. Just tell him Registrar ma'am came to leave this. And she's asking for suggestion of the date between 10, 11, 12, and 13 when the students have to go to this place. It's for blood donation, like last time we went. Thanks. Thank you. Thank you. Say register ma'am. Okay. Sorry. So, if the point comes in between two real poles, we call it as breakaway point. In the same case, if it comes between two real zeros, we call it as breaking point. Then we'll get a question, what if it comes between one real pole and one real zero? How do we call that?
It will come from poles and it will converge to zero
Hmm.
in a
Ah,
So I
yeah,
guess nobody,
that's correct.
nobody
But
can.
if there is some other pole lies here or zero lies here, except something is going to infinity, for example, here.
If any other pole is there, then Then in between both,
We don't really
both the
call it
poles.
with any names, right? It's based on
Okay,
the systems and how we are calculating about what point it is going. Based on that, we will decide.
depends on the system.
Yeah, right. Okay, we'll go ahead with our system. So we found minus 0.7, 0.8, and minus 3.2, right? So where is our root locus diagram? Here it is. I have pasted it somewhere, no? Okay. Okay. Now I found I found this point 0.8 minus 0.8 where it can come here somewhere. Minus 0.8 it can come. This will be minus 0.8. And I found another one is minus 3.2. 3.2 means here somewhere this is minus 3.2. Okay, so this first B1, B2 I'm calling. So this B1 comes between two real poles, right? So this is breakaway point. No doubts in this, right? So this will breakaway points leaves the real pole and goes towards the infinity or a complex
Infinite.
plane. So
Yeah.
this is going to break away and it is going to go in some direction to infinity following some direction. So this is how this direction is going to be since it is breakaway. So this is also in between two poles. This is also going to break in this direction. Right.
So here two breaking points will come now.
Yeah, right. So we have this here and
No,
it is going to break like this.
but the minus 3.2 is not valid.
Why why it
It's
is
not,
not valid? Oh,
it's
it's
not,
not in the root locus. Yeah. I missed that perspective. Yeah, right. You're right. So we are just leaving it. If it is not inside the root locus, so we won't consider that. That's it. So if it is here, then it will be the another breakaway point. Okay. Yeah, thanks for pointing it. Okay. Good. Then the one next point is to just um, plot the root locus. That's it. So we will have we found this no 60 degree, 300 degree, 180 degree we found. So out of this, which one is CC? 180 degree CC. So there is a root locus here. So one asymptote will start from this pole and goes till infinity at 180 degree. So this is one asymptote, the blue line. The rest of the asymptotes are 60 degree and 300 degree. So say 60 degree will come something like this. So this will go to infinity at 60 degree. So this will go to infinity at 300 degree. So if it is not clear, I will redraw it here. We have three poles, minus 2, 0, minus 4, and we found one asymptote that goes to infinity at minus 180 degrees. So I'm choosing this pole because it is going to infinity. And the next asymptote breaks at minus 0.8 and goes to infinity at 60 degree. And another goes to infinity, same. So around real axis, it is symmetric, right? So this will goes to minus infinity at 300 degrees Celsius. So these are the two asymptotes I found at the breaking point 0.8. So my root locus will do something like this. It goes to infinity since there are no zeros to track it down. Okay. Can we verify this using MATLAB?
Yes, ma'am.
I'm loading the MATLAB. Okay, my GFS will be K divided by. Okay, MATLAB doesn't know what K is. I'm just going to start with K equal to 1. So J is equal to transfer function of, instead of that, I can use this now.
Ma'am, screen is not visible.
Oh, I have present it.
Ma'am, it's visible.
It's visible, right?
No. The what you're typing is not visible.
Oh,
Okay.
okay. And then, okay, right. This, I can take it like this. We'll define like this. Is it visible now?
No, ma'am.
Still no.
No.
Okay. Are you like, is the MATLAB
Oh, yeah, the MATLAB.
portal is visible?
Yeah, that is visible.
Now I have increased the font size.
Yes, it's very big. Uh, mhm. This is okay. This is okay.
What is that? S into S plus 2 into S plus 4. Gayatri, is it visible now? Like for you, any issue you're facing? Okay, this is my transfer function, right? S square plus 6s plus 8 into S. Okay. Now I'm consider K equal to 1. We'll change K and C. R locus. The keyword to plot root locus is R locus in MATLAB. Just define your transfer function. We saw this how to define transfer function in different ways, right? So this is one of the way. I just mentioned that I'm going to use S as it is. So wherever I use S, consider this as a transfer function variable. This line will tell that. So I just wrote the transfer function as we defined here. It's easy to represent instead of calculating the whole quadratic polynomial and everything. Right. I'm just going to give this transfer function into this R locus and it will plot me the root locus. Okay. So is it something like we calculated? Our root locus plot was here, right? There are two poles, 0, -2, and -4. The poles are. And you can
Yes.
see this. I will see if I can increase the line with.
Pratham,
Yes, ma'am.
are you watching it on your mobile?
No, in laptop only.
Okay, I'm not able to see the screen.
Okay, there will be two of my ID. Try fixing that. You might be seeing one of the other IDs from my iPad.
One is your control engineering and one is your with your name.
Okay, I don't think I can increase the font size. Okay, if you can see, like you can see this, no? Is it visible? This root locus plot.
Yes, that one is
Somehow
60
for me
degree,
it's
which is
not
in
visible. I don't know why.
This is a 60-degree plot. This is the
green one is
300
your in
degree.
300 degree, and orange
Red
is
one is the 180
minus
degree.
infinity.
Yeah, right. So this is how we see. So if I this actually tells you changing the k from I have took k equal to 1, but this root locus started with k equal to 1, and it tells you
Okay.
by changing from 1 to infinity, this is how your root locus will tell, or your pole location will go. For example, so if I put this in a closed loop system, then you can track out of it. This root locus actually tells how your pole location or your what to say, your system behavior will look like when changing k from 0 to infinity. That's it.
So this system is marginally stable because its one pole is at zero also. Therefore, it's tending
System,
to positive infinite also.
I have to check. Yeah, it has 0 there, no? It will
Yeah.
be marginally stable. Yeah. 0
Hmm.
minus 4 minus 2, then it is marginally stable. Yeah. So small perturbation can make the system go from stability to unstable.
Hmm.
Okay. We'll solve few other examples also.
So this root locus will always, for a stable function, it's always tends to minus infinite or like infinite. Like here we
No,
see
no,
that.
it's not like it will tell. It will. We can draw root locus for unstable system also, but we won't be getting anything out of it. It's the system is naturally unstable. What we can do, if we want to design a controller, then we can think of it how we can pull the poles from the unstable region to the stable region. That you
To
have
the
to
stable
change
region.
the
Okay.
controller characteristics. Yeah.
Okay.
Okay. We will solve another one problem. Okay. So forward to present here. We'll see one more different problem. It will be little longer than this. It has one more steps, and we'll see why it has one more steps. G of a is h of s equal to k into s plus 3 divided by s into s square plus 4s plus 30. Right. This is your loop transfer function. Now, the first thing what we have to do, what is the first step of finding root locus?
Uh, for this, first we will find poles,
Number of
zeros.
poles, number of zeros, and where this pole and zero location. Right. So, how many number of poles are there?
So one is your s equals to zero, and one is
Just
your
number of poles.
minus one and three poles.
3 poles. So, number of zeros would be
One.
1. Right. The pole locations are 0, minus 2 plus or minus 3j. It would be 0 location is minus 3. Right.
It's
Now
four
you
s plus
know
13.
4s
It's
plus 13.
okay. Okay. Yeah, fine.
Okay. Now these are all your pole locations, right? 0, minus 2 plus or minus 3j, and zeros will be minus. Now you know you have pole 3, 3 poles, and you have zeros only 1. So out of these 3 pole, one pole, any of the one pole, I'm randomly choosing here. Any one pole will reach this 0. The rest of the pole will go to infinity. Right? 2 poles will go to infinity. So we have to find asymptotes of 2 values, right? 2 asymptotes we have to find. Then k equal to 0, comma 1. For 0 and 1, we have to find the asymptotes, right? This is the first step. The next step is to plot pole 0 and root locus on the real axis, where this your root locus will come. Now I am going to trace all the poles and zeros. One pole is in 0, another pole will be -2. Consider this as -2, -3j, -2 plus 3j, and -2 minus 3j. And I'm going to represent this 0 in terms of blue color at -3. Okay, this is my pole 0 plot. Now we will see. This song. Chair. Okay. Now we'll see whether like what are all the test points will be there in the root locus. We know we are experts now. There will not be anything here in root locus, so we are going to avoid that. Now I will check. If I take a test point here, one is odd number of poles in the right of, so that will come. If I take this test point, then also it will come because 3 poles will be there. So this entire point from here to here will be in the root locus vicinity, right? So if I take a test point here, it won't come because it will become 4. So only this portion from 0 to -3 will be in my root locus direction or else branch. Any doubts still here? Any confusions you have? If you have, just let me know here itself. We'll see 2-3 more examples here also. If no, we will move. Okay. The next thing is, what is the next step? Anyone can remember? We found the root locus now, or we know the root locus limits from where to where it will be there in real axis. Now we want to know which root locus is going to go till 0 and which one is going to go till infinity, right? So for that, what we have to calculate? Asymptotes, remember? So asymptotes angle will be theta equal to 2k plus 1. This is not 2 into k plus 1. Please don't make mistakes like me. N minus m. Your n minus m here would be 2k plus 1, 180. N is 3, m is 1, 2. 2k plus 1 into 90. Because 3 minus 1, 2, it will go take it away. K equal to 0, 1 because 2 poles are only going towards infinity. 2 into 0, this will give me 90. The another one will go at 3 into 90, it is 270. So these are all the 2 directions my root locus is going to. Right. Now, the next step is to find the breakaway or breaking point. Is it going to break from real axis to go to infinity? Most probably it will break, right? Because we have many poles than zeros. Break away or break in. How to find this? dk by ds equal to 0. We have to equate to k equal to and then dk by ds equal to 0. So if we equate, this will give me minus 1 by gsks. 1 minute. I've been sharing, right? My screen is visible, I hope. Is my screen visible?
Yes, ma'am. Your iPad is visible.
Yeah. Mhm.
Ma'am, how we find asymptotes as 0 and 1? Like k equals to 0 and
Asymptotus?
1.
Because we have one pole is going to 0, no? We have two other poles that goes to infinity. So only we can find for 0 and 1. If three poles go, we will find 0, 1, 2. Starts from
Okay.
0. You have to
Okay.
find,
In integer, in whole number, we'll
uh,
take from 0 to 1, 2, 3 as it will go. Okay.
yeah, right. So, right. For now, this will be 1 plus k into loop transfer function equal to 0. So if I want to find k, it will be 1 by L of s. So L of s, we know this is where it is. S plus 3. L of s is loop transfer function, that is g of s into h of s. S into s square plus 4s plus 13. See, this is my loop transfer function. So k equal to minus 1 into, oh, this will be 1 by s plus 3 by s into a square plus 4s plus 30. Solving this, how can I write it? S into a square plus 4s plus 13, 4s plus 3. This will give me. Can I split this into s plus 3? No, right? Not possible. So, right, I will just
No.
write it plus 13s by s plus 3. dk by ds. I think it will come in a larger. So it means equating this will give me 2s square plus 8s plus 13 divided by s plus 3, right? Yes. Oh, okay. I have to do uv for this. U by v. Because s is there both, right? duv, differentiation of u by v. It will give me s plus 3 v du. And this, excuse me. Maybe he's in Saturday. Minus 2 s square plus 8s plus 13 minus of v du. S cube plus 4s square plus 13s into du, right? It will be 1 divided by v square. You all know this, right? d by dt of u by v du minus u dv by v square. So whatever is there in the denominator, okay. Here denominator is s plus 3. That's it. This is dk by ds. So s plus 3 minus of 2s square plus 8s plus 13 minus 6 cube plus 4s square plus 13s divided by s plus 3 the whole square. Let us keep it like that only. Minus will be common. 2s cube plus 8s square plus 13s plus 6s square plus 24s plus 39 minus s cube plus common minus, no? Minus 4s square minus 13s. Everything is minus here. Then this will be all I take, all minus I'm taking common. 3s cube plus 14, 10 square. Please calculate along with me. I might make mistakes. 8 square, 14 minus 4, 10. Plus 13, 24. 27, 37 minus 30. Okay, this 13 and this 13 will get cancelled. Plus 24 is plus 39. Okay. Okay, good. Minus of 3s cube plus 10s square plus 24s plus 39. This is my final. So by s plus 3 the whole square always comes. S plus 3 the whole square. dk by ds equal to 0. If I equate it to 0, this denominator will go away. S cube plus 10s square plus 24s plus 39 equal to 0. So if I find, I will use online software and find the values out of this. Just giving me somewhere around 0.64 and some value minus 4. And that would focus around 5.6 something. It's giving. I might make mistake here. Okay, please check this. So out of this root locus, only that 0.56 around 0.6 around I'm taking. Minus 0.6 is in the root locus location. So I am going to take that as a breakaway point since it is between two roots, two poles, sorry. Okay, then check. Minus 0.6 somewhere here. It's my breakaway point. Okay. This is going to break and here it's going to break and go to infinity via that pole. Oh. Shouldn't be like this, no? Okay. I verify it once. Okay, right, good. So since we have complex pairs of poles, we need to find an extra step here. Another one calculation should be here, fourth point. So this will be fifth one. So calculate the angle of departure. So for all problems that has imaginary or complex roots, we have to calculate this one extra steps. This tells you how branches leaves complex plane, complex poles into complex planes. So the similar to this what we saw, it's a asymptote, right? It will tell how the root locus leaves the real axis into the complex plane. This angle of departure will tell how the root locus leaves the complex poles into the complex plane. Just real to complex plane. Here this is complex poles to complex plane. That's it. That's it. In case of real poles, we'll have to find asymptotes. In case of complex poles, we have to find the angle of departure. So angle of departure will be found using this formula 180 degree plus summation of angles from other poles minus summation of angles from other zeros. Okay, so this will help us determine that. Can you solve? Can you solve and let me know? If you need any help, let me know. Just find it. This other poles, 0, -2, -4. Other 0 is mainly -3. How can we find it?
What are the poles, man? What
What?
the poles?
Yeah. 0 minus 2. Oh, sorry, this is different, no? 0 minus plus or minus 3j. Yeah? What I found. This is previous one. Plus or minus 3j. So these are all the poles. 0 is in the minus 3. Consider P1 equal to 0, P2 is equal to -2 plus 3j, P3 equal to -2 minus 3j. And determine 0, z is equal to 3, only 1 0 is there. So first find angle from P1 to 0, one of the poles, sorry, P1. Some point, you take some ordinary point like this from this breakaway point and find till 2P1. That is the first pole, 0. Let me write it clearly. First, we need to find angle from a point P1 to P to P1. That is 0 here. 0 is one of the poles, right? So the P1 point I'm going to take instead of here to the one of the poles location. That is -2 plus 3j. First, I'm going to take my P equal to -2 plus 3j. My P1 equal to 0. Just calculate the angle between these two. Angle between your P1 and P. That's it. Angle can be found like this. Since it is a complex force, you can find this from your calculator. Otherwise, if you are using online, you can find it using a tan 2 of your imaginary comma real. Since it's another pole P1 equal to 0, you have only 2 minus 3j minus 2 plus 3j only. So if you find it, it will come around minus 56 degrees. If I take another P, minus 2 minus 3j, P1, same P1 to 0. Here I will consider P2, that is the another pole pair. Same from P to P2 will be minus 2 minus 3j. Okay, I'm taking like this. There is one pole, another pole is here, another pole is here. Here it is the breakaway point, and this is my 0. Okay. First, I am considering this as P, and I'm finding angle between P and I'm finding angle between P and P1. This is P1, P2, P3. So considering P2 as P first, I'm finding angle between these two, that is 56 degree. It measures around 56 degrees. Now I am going to find angle between P2 and P3. That is, we know we don't need to calculate. Even if you calculate, you will get 90 degree out of this. Now we have to calculate the same point from P to Z. This angle I want to calculate. So the same formula. Now considering P equal to minus 2 plus 3j, P3 is my zeros location, Z, or P instead of P3 you can put Z also. So your angle would be 0 minus P, so not 0, right? Minus 3 minus P equal to angle of your minus 3 minus 2 will be minus 1 minus 3j. If I calculate a tan 2 of minus 3 comma minus 1, I will get what I will get. I'm getting around 108 degrees. Okay. Now we are going to club all this degrees we found. This, and 90 degree we found in between, no, between these two. These three we are going to club together in the formula, that is pi equal to 180 degree plus summation of angles from other poles, plus summation of angles from other zeros. So 180 degree minus what I found, 56, right? Plus 56 degree minus everything is plus here. Oh, this is minus 1. This will be minus, okay? Minus of minus 180 degrees. Okay. 108. Put 108 minus of 108 degrees. Calculated. So this will entirely give me 142 degrees around. I'm getting. So this is my angle of departure. At this angle, it will depart. So if I see my rule locus, What are you looking for? 0, another pole, the location. So this is my root locus. So from here, this this is departing minus 140 around here. It will goes to infinity. So this will goes to infinity at this location. Right? Okay. So we can verify it using MATLAB. Since we are running out of time, we can see some other problems also and some like small problems but intuitive problems we will see. Fine. Okay. Out of these three, can you find the valid root locus diagram? Which one do you think valid?
Both. I think A and B are valid.
A and B are valid. Why?
The locus goes from pole, starts from pole to ends in
Open
zeros.
loop poles to open loop zeros. Okay, right. Now, this is correct. And since this is starting from open loop zeros to poles, so this too cannot be the option. But this is not MSQ, this is MCQ. You have to find one out of A and B. How to judge between A and B?
Stability
What?
means
Wait. I
one is
missed.
on.
Yeah. I missed a part. Wait. With that only you can say.
Okay.
Okay. Since we ruled out C and D, that's okay. From here you tell.
So should we look for the angle of departure?
Exactly. You have to look on the angle of departure. Based on that, you will tell. A is the correct answer. You can check for it later. Just look for the angle of departure. That's it.
How, ma'am? Like, so,
Calculate this theta equal to 180 minus 180 degree plus sum of angles from poles plus minus sum of angles from zeros.
okay.
So zero, we don't have exact value, just put some arbitrary value. So let's take this as if it is minus 1 plus minus 1j, it might be minus 4j kind of. You can arbitrarily take just a intuition, right? Based on that, you can find. It's only angle, you don't need any values for it. Okay. Next problem, we'll see. Okay. I'm giving a loop transfer function a into s plus 2 by 3 divided by h square into s plus 2. The options are yeah, yes, one something. Yeah, yeah. What?
Oh, uh, I was in with the professor.
Oh, professor will come a little late. I think he might be in faculty meeting.
Oh,
Okay. The first options are three roots with nearly equal real parts exist on the left half of the S plane. Second option is one real root is in the right half of the S plane. I'm writing in shorthand notation. If you don't understand, ask me. Root locus or root loci cross j omega axis for a finite value, some finite value, at some finite value it is crosses of k when k is not equal to 0. Three roots are in the right half of the split. So with this, how can you come to a conclusion? Any property based you can recollect or anything you can think of. It won't need much time to solve, but technically you have to think, that's it. This is open loop transfer function with unity feedback, not g of s into h of s. You should be careful about that also. So if it is a unity feedback, let us solve this. G of s and h of s is just into one, right? So that same transfer function will come. If the unity feedback is not unity, then you have to multiply that with that. Since it is a open loop transfer function. I hope that is clear. First, what we will do, we will find the poles. So poles will be 0, 0, minus 2. Zeros will be minus 2 by 3. So we'll plot the root locus. Quickly we are going to do. Two poles are here at the same location. And one is at minus 2 and 0 is at minus 2 by 3. Okay. I will use same color here, otherwise it will be confused. Two poles are at the same location. Okay. This is so out of this, if I want to find the root locus, this will be in my root locus and this is in my root locus. These are all the two root locus directions. After that, what I will do, I will find from for asymptotes.
Ma'am, one doubt.
Yeah.
So when you say two poles on 0,
Ah,
so that the points
yeah, that
at
will be calculated. Yeah, yeah, right, right. I'm understanding what you're trying to say. I don't remember that there exists two poles. So these are like silly mistakes we do in exams. So these are two poles, right? So there is -2. If this is -2/3, -2/3 will come before that -2. -2/3 means it will be
like 0.67.
0.6. So I'm considering this. So this is -2, -2/3. This is 0. That's it, right? So if I consider this won't come under root locus. So this will be in root locus. Only this will be in root locus, right? -2/3 to -2 will be in the root locus. Other than
Yeah.
that, nothing. Okay. Now we will find the breakaway break-in points, right? How do we find theta equal to 2k plus 1 into 180 by m minus 1? Before that, there are three poles, 1, 0. So 2 goes to infinity. Two poles goes to infinity. So we have to find two asymptotes here. So it's k equal to 0, 2k plus 1 into 180 divided by 2, 2k plus 1 into 90. When k equal to 0, this is 90. Again, it will be 180, right? When it is 270. 3 into, right? So it will be 270. So the two asymptotes will go at 90 and 270. Okay. So we should calculate centroid to find exactly from which point it will go. Sum of poles minus sum of zeros divided by number of poles minus number of zeros. Sum of poles will be 0 plus 0 minus 2 minus of -2/3. So plus 2/3 divided by 3 minus 1, 2. So this will be minus, how it will be? 2/3 minus 2 means -4/3 by 2. So by 6 minus 2. So centroid would be -2/3. Exactly at this 0, it's going to separate into two different quadrants at this point. Okay. Then the next step is to find the breakaway, break in. How to find dk by ds equal to 0, k equal to -1 by l, k equal to 1 by, instead of writing 1 by l, I can write the same thing. So when you keep on practicing, you will also get to solve it at a speed. You can complete it within the time. Just you need to solve just before the day of exam, it won't work. Dk by ds. So before that, k equal to minus of s cube plus 2a square divided by s plus 2/3. ds will give me minus s square plus 4s divided by s plus 2/3. So it is 0. So this will give me 3 square equal to -4s. 3 is equal to 4. S equal to 4/3. And s equal to 0. Correct? These are all the two breakaway breaking. So out of this, 4/3 comes in the root locus, I guess. 4/3 means it's further down, right? 1.33. Yeah, here it will come. So I'm taking 4 by 3 is the breakaway point. Or breakaway or break-in, we cannot tell. It's between real 0 and real pole, right? So I'm going to
Ma'am, what is
point
the
it.
purpose of centroid? Ma'am?
Centra is exactly this breakaway tells at what degree it is going to separate. Centra tells at exactly in the real axis from what point it is going to separate. So it can be from here, here, anywhere, no, the same asymptotes. But exactly from which point it is going to separate, we have to calculate using the centroid. So here we found from this point it is going to separate at 90 degree and 270 degrees. Okay. We made a mistake here, no? This is again a U by V method. I just overlooked it. We cannot straight away equate it to 0. We have to do it by how we did in the last problem. So, while differentiating, this should be considered as a U by V. So it will be S plus 2 by 3 into minus 3s square plus 4s minus of s cube plus 2x square into 1 divided by s plus 2 by 3 the whole square. So it will be 3s cube plus 4s square plus 2s square plus 8s minus s cube plus 2s square. S cube minus 2s divided by s plus 2 by 3 the whole square minus 4s cube minus 6x square. So it will be plus, oh, again 8 is there, no? 8 square plus 8 is, it will be 4s cube, right? It's supposed to be 6x cube. Three is cube plus 2 is square, that's right. Plus 4 is square plus 4, 8 by 3. Ah, 8 by 3 is, no? Three is cube plus 4 is square, that's right. Plus 3 will get cancelled, 2 is square plus 8 by 3 is, that's what I meant here. Minus s cube minus 2 is square. If I take s as common, 3 is square plus 6 is plus 8 by 3 minus s square plus 2s by s plus 2 by 3 the whole square called right. If I take another 2 is common, 3 square plus 6s plus 4 by 3 into, if I take 3 by below whole square. Ultimately, and equating to 0 will get me 2s, 3s square plus 6s plus 4 equal to 0. This will give me s equal to 0. And s square plus 2s plus 4 by 3. We calculate this will give me minus 1 plus or minus root 2 by 3j. Okay, so these are my points. This what is root 2 by 3 now? 1.4. 5 minus 1 means minus 0.44. No. Minus 1 plus or minus 1.4. So that will come here anywhere. Minus 1. Minus 1 won't come inside, no? It will. So here somewhere the breakaway and breaking point. How come it is not coming inside 0.4? It is included, no? Oh, okay. Since we don't have any conjugate poles, this breakaway breaking point is not valid here. So we are going with only this. So I'm going to take only s equal to 0 is my breakaway point. Because we have poles here, no? Just as in the pole, it is splitting up. It's going breakaway and going to infinity. Taking a break and breakaway point, considering it as a breakaway point and going to infinity. That's it. So if you draw this, you will get the root locus out of it. What was the question? The question is out of these three, what do you think will be the correct three roots with nearly equal real parts exist on LHS? No, because two are in origin and one is in -2. One root will be here. One real root will be in RHS. No. Root locus cross the j omega axis at finite value. 3 root in the RHS. So this is going to be the correct one. Can you write the transfer function of this pole zero plot? Zeros lies in S minus of S plus 1 plus or minus j. Poles lies in S plus 2, S plus 3. Right? So this could be one of the questions you would expect. Now I can ask find the breakaway and breaking point. Breakaway or breaking point. This can be one answer. Just you need to find. So add k here for loop transfer function g of s h of s. Then equate k equal to 1 by s plus 2 into s plus 3 divided by s plus 1 plus or minus j. s plus 1 plus or minus j. Then do dk by ds and equal to 0, and you would find s is equal to some values. Two values you will get because this is a second order function, no? So you can choose which one is a valid out of the given answer. You can choose the breakaway and breaking point from this. This is one potential question. The next question is we will give root locus plots and you will be asked to find the valid root locus as we did in the first question. Or we can ask you us to find breakaway, break in. We can ask you to find the angle of departure, centroids. So these are some potential problems you can look from the root locus. Otherwise, we can ask when k equal to infinity, if we give a g of s and h of s, and when k equal to some value around 10, how the root locus or where the pole location would look like in the root locus. Or we can ask, we have this many poles, this many zeros, and what points will have in the root locus. These are all some questions you can expect out of the root locus problems. So you can prepare for the exams in this direction. If you have any doubt, you can ask. Otherwise, we can wrap up the session. If no, we can finish the session. Right? Thank you.
Yeah. Yeah. Thank you, ma'am.
Thank you.